Hello, this is part two, and I'm going to start off where the first part left off. So, if you look at the human growth curve, the human lifespan, you'd see that there's a maximum parental investment. That means the human baby lives with the parent the longest of all species known to mankind right now. So, since the parental investment is higher, the infant mortality rate is much lower. And then when you look at mollusks and things that have that have a lower parental involvement, the death rate when they're really young is much greater. Here in the case of the squirrel thingy, there is parental investment, so you see like a straight curve. The other thing out here for human beings also, the reason why these two guys have slightly the similar infant mortality rate is because the fertilization takes place inside in vitro, so there's a better chance that it's going to survive. Whereas if you look at mollusks, they give birth to their babies by dropping the eggs in the water and sperm in the water. So large number of eggs have to be produced, and large number of sperm has to be produced. There's no protection in the first a few months of the animal being a little baby, and it goes through a larva stage. So there's tons of predators, hence their mortality rate is much greater. You'll also see that once they hit like their 50% mark, they tend to die off pretty easily. We're going to look at the next part is reproductive rates. This is pretty self-explanatory. It's looking at what age-specific reproduction. Obviously, like if you take a human being age specifically, the reproduction is greater between the ages of 20 and 45, 50, and 50 nowadays, because you can have babies after that. 40 is actually my bad, 45 is too high. Between 20 and 40, there's a higher chance of there's a higher reproductive rate, and kind of falls off after that. Women can have kids after the age of 45, but there are tons of problems with that, and we'll talk about that when we talk about reproduction and stuff like that. This is kind of a table that explains that. I'm not going to expect you to know all of these numbers. Just remember, most organisms during their prime are going to be more reproductively active. So if you take a human being, they're more reproductively active between 20 and 40. That's like their prime years. After that, it becomes a little more difficult. Think about just in terms of how much parental investment is required to take care of a baby, it kind of tapers off, and you'll see that in the squirrels also. Okay, when we talk about how reproduction takes place, there are two different things. Simulipatry, or Big Bang reproduction, that is, it reproduces once and then just dies out. There are certain plants that do this. The plants that are annuals, or the ones that live for 1 year and then die out, they reproduce just once, large number of seeds, and then they die. There are animals that do that. For example, salmon only spawns like once in its lifetime. It goes upstream and then it spawns and then dies. That's simulipatry. Human beings like us, we are heteropatric, sorry. That means we have repeated reproduction. There are a couple of benefits to this, so let's go back and look at it. If you have simulipatry, this usually happens where a large number of seeds or a large number of eggs are produced, and so survival is based on that one spawn that it lays. So competition is between the little the babies. So that's where the competition is. Now, one of the benefits of this is that there's not a large investment. The trade-off is the amount of investment that the organism has to make to produce these eggs at one stretch, or produce these seeds at one stretch, is lower, since the organisms don't live that long. This is a trade-off that they can do. Plus, they also, since they only produce one stretch, the eggs are pretty much genetically identical, and some would argue that's slightly stronger than animals that produce many times during its lifespan. In the second case here, the trade-off is that it does have a huge energy investment, but since it's able to do this reproduction few times within its lifespan, it can basically correct its mistakes. So let's say you had a lion that's reproduced with an X male, and then 6 months later it finds the female finds a male that's stronger. Now she is capable of producing stronger offsprings. So that is the trade-off. Natural selection takes place in both cases. A certain amount, a great portion of the selection is done by the parent. In the second case, in the first case, selection is basically straight competition between the offsprings. Please remember that is going to be a question on your test. Similar patry is going to have competition for resources and natural selection happening between the offsprings. The parent is removed from this equation. Now, that does not mean that a stronger genetic parent would not produce stronger eggs and stronger sperm. That's going to take over, but still competition is just between the offsprings. On the other hand, heteropatry is a certain amount of selection is also done by the parent. Mate selection plays a vital role in the second case and not so much in the first case. In the first case, 99.99999%, because with certainty we cannot say it's 100% because we don't know all the species. The eggs are laid in one place, and then the sperm is laid around that same place, and they have to find each other. Same thing with, whereas with plants, they could be cross-pollinated or self-pollinated. We'll get to that later. Now, so far I've talked a little bit about trade-off. Everything in evolution, in nature, is a trade-off. So if you're going to have, like when we were talking about co-evolution, why is it that animals don't run at the speed of light? Because as the prey gets faster, the predator gets faster. But it's not an endless pursuit of eventually running at the speed of light, because there's so much energy is required for that every extra foot that a plant grows, or every extra mile in speed that an animal gains. Mile is too large a distance here, but just so you know. So if you, this is also the case in terms of brood size. How big your pack is depends on the resources you have. So if you have a really large size of a brood or pack, or even in this case, let's look at a brood. That's since they're indicated. So a brood will be how many offsprings it has. If you have a parent who has too many offsprings, then while their genetic material goes to the next generation more effectively, it doesn't mean that the next generation is going to survive at the same rate. So I mean, think about it. Normally, if you have limited income and you have 13 kids, some of them are going to suffer without food. Whereas if you had limited income and you had only 2 kids, you'd actually be able to provide more. So reduced brood size actually helps in heteropatry. It actually helps the organism be stronger and have a better survival rate. But at the same time, if you have a large brood, if you look at man's evolution in the beginning, early man, when he was learning agriculture and all that stuff, it made more sense to have a lot of babies. Why? Because they were able to, even if some of them died, you are able to reproduce many number of times, so it doesn't matter, and you got free farm hands and free help with war. If you were warring between 2 clans, you needed people, so you could create your own people. Excuse me. So everything is basically a trade-off depending on how much resources you have, what is your needs, what are the kind of what are the resources that your little brood needs. If there is any kind of huge environmental shift, that's going to make a change, that's going to impact your brood size. So it's not, there's no hard and fast rule as to what the brood size should be, at least for human beings. So in case, again, we've talked about this in the past, in terms of plants, it's very important, especially plants that are being pollinated by wind, where, you know, the seeds are spread across a certain area by wind. The word pollinated is not right. Where the seeds are dispersed by wind, you are going to need to produce a large number of seeds because you don't know exactly how many of those are going to survive. So the investment on the part of those plants is going to be huge. They're going to invest a lot of their efforts into just getting seeds. You'll also notice that some of these plants are going to be much smaller than other plants because most of their investment is going towards making seeds. The other plants that have usually large seeds, huge amount, they're able to store a large amount of food in them, and they're not dispersed by wind. Sometimes they're dispersed by water. So if they're dispersed by water, also it requires a large number of seeds, but they will produce a moderate number of seeds because their growth is, their methodology is pretty targeted. So just like I was talking in the past, like parental care for smaller broods. If you have a smaller number of offsprings, chances are they're going to survive better. The survivability of that offspring is better. Now, this is in direct correlation to your parental investment. If the parental investment in raising the child is greater, that group, that species benefits from having smaller broods. That is, for human beings, the parental investment is very high, so we benefit from having less number of children. So I'm not going to go over the exponential model of growth right here because, frankly, we've talked about immigration and emigration and how it works. I don't need you to know this, so we're just gonna, I'm gonna ignore this part. Exponential growth, the part that I need you to know is this portion. Just be able to figure out what the growth curve looks like, the J curve. What does it mean? And I have done this in detail in your environmental science class, so you should know this. What does it mean to have a J curve? What does it mean to have an S curve? Also, remember, in terms of human populations, what is the carrying capacity of the population? What does that mean? You kind of need to know these things. Again, these things have been dealt in detail in your AP Environmental Science class. You guys have also done a little, like a paper thing, like a project kind of thing on this, so you should know that. Carrying capacity is the maximum capacity that a population can support. So when we're talking about maximum potential, we're talking about individuals that can reproduce. So this usually has a range. So if anything falls below the carrying capacity, the chances are it's going to die pretty soon. It's going to go extinct pretty soon. If it goes above the carrying capacity, that's not a good idea either. Then that's when you start having a lot of disease, and because overcrowding takes place, and then you also have death. So carrying capacity, I'm not, K stands for carrying capacity. I don't need you to know this, so don't even worry about that. I'm not going to expect you to know this. What I do want you to know is the fact that human growth right now is exponential. So the J curve shows exponential growth, and then when you have an S curve, you're seeing a logistic growth. Be able to, the S shape, we've talked about this. This is where this like little curve here is the lag phase. You have the log phase that goes up here, the stationary phase, and after a certain point of time, the stationary phase starts to dwindle down, and you have a death phase. Please look through your AP Environmental Science notes, and you will find a lot of information about this. Okay, I'm going to end with this slide, and I'm going to get back to the slide because I'm running out of time.